Hey guys, welcome back. In this video, I'm going to give some basic introduction to R, and I will learn how to perform some statistical analysis. Okay. So first of all, I want you to go to our Brightspace course. Go to course home and click on sample R code. Right. So I post all the introduction R code here, all the R codes. And then later when I finish recording this video, produce it, I will post it here so you can use it to learn for the contents. So you click on introduction R code and you can download this. And we're going to run through all this code one by one, and then I'll try to explain all the details behind it. So you open this, and also I want you to go back one more time. Just going to show you how to import a data set in a CSV file into the RStudio. So you're going to download this emission dataset and click on download. It's a CSV file. So first of all, let's open RStudio. So once we get to the RStudio, we can start analysis. Okay, so in the search bar, just type in RStudio and open the software. Okay. Once you open that, this is typical interface of RStudio. So now here, first of all, I'm gonna show you how to get an R script, right? So we're gonna code under the R script. Okay, so just go to new file and then click on R script. See that? That's one we are using. And right here, you're gonna see it's located above of the console, right? This is the console, and then this is R script. And then first of all, you can save it. Let's say save it somewhere. I'm gonna save and download. It'll be called introduction to R code. Okay, and then click on save. Right, it'll be saved. You can constantly save this R code. So that's one thing I want to show you. And then secondly, you can import a data set. Import a data set. You go to import data set, and then from text, read R. Okay, and then here you click on browse, and then under download, I save it under download emission data set, and click on open. And then as you can see, the most important thing is in this bar it says cannot find instructions. Yes. So just make sure the name is emission. Okay. And then let's see. Click on imports, right? And I should be able to see all this. You see the data sets imported. We get a 4 columns with a different variable name, emission, GRE score, GPA, rank. So those are the how to import a CSV file. Okay, now I'm gonna delete it. Right, we don't need it for this particular section. And our next thing is I'm gonna show you some useful tips to modify the settings here. So you can go to tools under global options, and here you can basically change the code settings. There's code settings. You can change how the code displayed. Okay, and then you can, let's say, highlight selected lines, and then formatting. If you like to certain formatting, you can modify here. Right, I'm gonna leave it as default for now. And then also consoles, right? You can modify the consoles here in this particular icon. Appearance, and so basically that's a different kind of like editor things, right? Ambience, right? Something like that. I'm using the default ones, but you can pick the one you like, right? Depends on your preference. A lot of different kind of like environment or like theme editor thing available. So I'm gonna just stick with the default ones. It's called yeah. So I'm gonna stick with the default. Yeah, Chrome, right? That's the default. And then apply. It will. See, once you apply, implementing the particular thing. And under the pane layout, you can also modify the pane layout. I specifically designed this pane layout like this. So R script on top, console on the bottom, and also the environment history, I put it on the right on this side, on the right hand side. So left hand side is R script and also the console. On the right hand side, it's files, plots, right on top, and then packages, environment history, files, plots on the right hand side, top right corner. The bottom corner is packages, tutorials, viewers. That's all. And click on apply and then OK. Now this is a typical our interface, right? Let's say you want to just focus on the coding block or R script block. You can just press this, and this one will console will disappear right, for a second. If you need it, just click on the icon right next to it. It will show up. Again, we're going to press for now. And then typically, we just put in a code in this R script and on the top right corner, that's environment history. History has kind of like different kind of anytime we type in, see, we just install the CSV file right earlier. So show up all the code will show up here. Okay, now we just clear all the histories. There's a file. Let's say you want to import a certain file, you can go from here as well. Right here, you can type import text files, different files right here. And also the plots, right? That's most important. I'm going to make it as a default because we're going to analyze a lot of different graphs in a second. On the bottom right-hand corner here, you see help, tutorial, viewers, packages. So different packages you need for different purposes. And we will go over some of the packages throughout the semester. Also tutorials, and you can just click on that and take you to the tutorial sections. And also viewers, right? Let's say you want to suppress this. I'm going to suppress it because we don't need it too much for now. So let's start with analyzing the MPG dataset, right? If you want to see the title, you can just get it from here, right? I'm just copy that from our documents, and I'm going to paste it here. Right? So the first thing is we analyzing the MPG dataset. Here we install packages first. We're going to install this package called ggplot2. This is a very popular package. We can create a lot of nice graphs, fancy graphs using this package. And also, once you type in this, we also need to activate a library of ggplot2. And also, in order to use the embedded data set, there are a lot of embedded data set in RStudio. I'm going to use some of them. One of them is called, the one we are using for now is called MPG dataset. So library datasets, meaning we tell in the RStudio we are using all the data set embedded in RStudio. And also, let's run this 3 code first, right? Run this, you see, and then once you just I don't think you will. Let me run the code. I'll just delete the title over there. Run the code one at a time. You see, it's executed down below here. You see, in the backend, RStudio is executing all these codes, right? The next thing is run the second line of code. Run And then also let's run a library. And as you can see, it's being executed. Okay. Now we're gonna analyze this data set called MPG data set. So you put question mark MPG. Anytime you put question mark, on the side you see, and let's run the code. Down below here. Okay. And as you can see, this under help, it will give us a brief introduction, give us information about the MPG dataset, right? So this is the fuel economy data from 1999 to 2008 for 38 popular models of the cars. Right? You can click on this EPA. It's from the EPA website, right? You click on it, you can see the original source of the dataset, and then basically the format is data frame with the 234 rows and 11 variables. We have different manufacturers, models. BRSPL is a displacement, engine displacement in liters, and year of the manufacturer, cylinders, number of cylinders, type of transmissions is either automatic or stick. Right? And DRV is a type of drivetrains. So we have different kind of drivetrains like front wheel drive, rear wheel drive, four wheel drive. CTY is a city miles per gallon, and HWY is a highway miles per gallon, and then FL is a fuel type, and then class is different type of cars. So basically, if you need to know the background information, you can get it from here. I'm going to suppress it for a second, and now go back to plots. Okay. Now next code, we're gonna take a look at the head. We can create this code called head of MPG. So it will basically show first 6 rows of the data set. So this is Audi A4 with the 1.8 displacement, 1999, 4-cylinder automatic transmission, and then front wheel drive. City mileage is 18 miles per gallon, and highway is 29 miles per gallon. Okay. So that's basically, and then it shows you the data structure of this data set. And yeah, I'm going to press it again, and then go to, if you do type in summary of the MPG, and then click on run. And you're going to see the summary for each variable. So we have different variables. Manufacturers, first variable 234 is a character variable. Model, it's a character variable. And displacement is a numerical variable that gives us a 5 number summaries together with the median, mean, right? Minimum for quartile 1, first quartile is quartile 1, median quartile 2, mean, and also the quartile 3, and also the maximum, right? Those are the 5 number summaries. And then our main focus is the CTY, right? We'll analyze CTY variable in a second. So minimum is 9 miles per gallon. Q1 is 14 miles per gallon. Median is 17 miles per gallon. Mean is 16.86 per gallon. So the mean and the median are very close in this data set. So we probably will assume this is a normally distributed data set. And then quartile 3 is 19 miles per gallon, maximum 35 miles per gallon. So you can examine each variable in detail. And also, let me see anything categorical. Yeah, looks like DRV probably is categorical. We will take a look at that in a second. So I'm going to suppress it. Now let's say you want to find out the mean of a certain variable, right? MPG $. Let's say the CTY. Let's look at the city mileage here, 50 miles per gallon. So as you can see, the average is 16.85897, right? It's displayed down below here in the console. And also, let's say you want to do a median. quick median here, median, same thing, MPG, dollar sign, dollar sign indicating we have specifying the individual variables here, so again CTY, and you will run code and show us the median here. And also variance, let's say you want to do a quick variance on the CTY variable, MPG, dollar sign, VAR. Not VAR, and CTY. And basically, it will show you this variance for the variable CTY. So basically, if you want to type in the code in the console, you can also do that. But I'm going to keep it consistent. So $sign CTY. You can run it here, right? You will show variance here. And also, let's say you want to do a standard deviation SD, MPG, $sign CTY, and run the code. Actually, 4.255946. You can also just type in the code in the console here. Also, it will show you the result. So I click on MPG, $sign CTY. Yes. So it's 4.255946. All right. And next, we will do an interquartile range, right? Meaning Q3 minus Q1. You can also do that. Interquartile range, MPG dataset for CTY variable. Okay. And let's run it. Okay. And it turned out to be 5, right? Q3 minus Q1 equal to 5 miles per gallon. And we can also do minimum. Also see that earlier from the file number summaries. $sign CTY. It should be 9, right? Because we run it earlier. It should be 9. And also maximum. We also do a maximum. I think it's 35. Let's see if this one confirms. Sure. So CTY. Run it. 35. That's exactly the number we are looking for. We can also do a quick range, right? Range of the MPG dataset. $sign CTY. Okay. Look at the variable CTY. And then the range is from 9 to 35. That's exactly. Now, next thing we will try to create a histogram, right? Based on the CTY. So the quick way to do it is just typing histogram with the first 4 letters, MPG, $sign CTY. And if you run it on the side, you're going to see this, right? The plots will show up on the side, and if you want to see a bigger graph, you click on zoom, right? And it will give us a separate screen with a much bigger graph. Look into this data set, we can fit the curve here. Looks like the center is somewhere around, maybe somewhere around this, right? 15 to 20, right? Somewhere around that. This is where the center is located. Most likely somewhere around 17. And also, because we have a much longer right tails, right? Slightly longer right tails, so this is skewed to the right. A lot of data values are concentrated between 10 and 20 miles, right? So this is our first impression about this histogram. And then we're gonna close it. And then if you need to copy this, you can export it, copy to clipboard, and it will show up here. Then you can just copy plots, and then you can paste it. Or I can even export it as a PDF file or as an image, right? If you need it. And then second thing, we're going to put in a little bit more arguments. So still based on the previous code. Histogram, we still focus on this, but we're going to put in a lot more arguments, CTY. Now the XLab, we can put in miles per gallon. Y variable, Y lab, It's one variable. It's called frequencies, because on the histogram is about frequencies. I'm going to press it. And then main is title. I'm going to type in histogram of MPG dataset, and just for city mileage. And then breaks meaning how many boxes we want, right? I'm going to click all boxes here. Color, indicate what color we want for those individual rectangle box. I'm using this called Alger Blue. And then border, put a different color for the border. And I'm going to use this color called dark orange. And you basically, whatever you type in the color code, right? The exact color will show up. And let's see how that looks like. See, this is the way it looks like. Again, it's a much better graph. Now we probably see, it will probably give us a much clearer picture about the distribution, also the center. Right? So right here, center probably somewhere here, Okay. And then the distribution still skewed to the right, but this one has a little bit more details. Give us much more confidence about the skewness. So there's a skewness here, skewed to the right. Meaning a lot of data values are concentrated between 10 to 20, right? Those are where the majority of the data value is. So I'm going to surprise this for a second. Yeah, let's go back. Now let's create a bar. Next thing, let's create a bar plot, right? Bar plot, still with the same variable. And this one, I'm going to create a table based on the DRV and PG. Dollar sign DRV. All right, and if you run the code, you will see, run it. So the graph pop up on the side, right? Let's take a look at that. Zoom in, see what happened on the table. As you can see, so we have a four-wheel drives, front-wheel drive, and the rear-wheel drives. Look like front-wheel drive has the largest frequencies here. So probably somewhere around 100, 105. And then four-wheel drive is a little bit over 100. And then the front rear-wheel drive is probably somewhere maybe around 25 to 30, something like that. Yeah, so that gives us a breakdown, right? So this is the categorical data values with 3 different categories: four-wheel drive, front-wheel drive, rear-wheel drive. So we see a clear breakdown. Now let's creating a slightly, and you can also suppress this, right? Let's say you want a bigger, you can suppress that. Okay. So now here I'm going to create a better graph, bar plot. Still using table, and here just putting a little bit more arguments. DRV. And here I'm going to give a X lab, which is X-axis. It's called drive track. And then we have 3 different categories. F is front-wheel drive, FWD, front-wheel drive. R is lowercase r is rear-wheel drive, and 4 is four-wheel drive. And now I'm assigning a y-axis title. Its frequencies, and name, which is subject. Color, using blue, or you can do dark blue, right? Probably should show up. Border, let's say dark green, light green. And let's see how that goes, right? Let's run the code. So we probably will get a slightly better graph if we see how this title here, x-axis, y-axis. Yeah, I'm gonna just close it. I'm just gonna modify something. I think that's missing. But you can always modify this code by close the parentheses here. Okay, I'm gonna run the code one more time. And zoom in. Yeah, it looks like just with much better details here, but still give us the identical picture. Yep. So now let's create some box plot, right? So box plot is important graph. So let's create box plot from a CTY variable CTY and pg.sign CTY. So this is a very raw data, a very raw graph, right? Run it, give us this box plot right here, and looks like so. In terms of reading this box plot, actually, this is the minimum. This is a Q1. This is the median, which is Q2, and this is Q3, and that's the maximum. So we have 4 outliers here. This open circle means outliers. So actually we have modified box plot and to the 40 outliers. So it looks like the minimum is 9, right? And maximum is somewhere around 25. And that's 35, and then anything above 25 is considered outliers. Our median is 17. And then Q1 is somewhere around 14. Q3, it's close to 20. So if you look at this box plot, it look like it's normally distributed, right? Center is somewhere around 17, and then it's normally distributed. That's what we see from the box plot. And again, we can put a box plot with a different format, right? So like this, CTY, curly wave, DRV, create box plot based on 2 variables, CTY and DRV. Data is MPG. Let's see how that looks like. All right. And basically, it gives us the miles per gallon based on 3 different drivetrains, right? 4-wheel drive look like this, front-wheel drive look like this, and then rear-wheel drive. And if you look at the 4-wheel drive, looks like it's probably somewhere close to normally distributed, right? Because it's almost symmetrical. Not much skewness, but that's a little outlier, one outlier here with this open circle. And then for the front wheel drive, there's several outliers, 5 outliers on the high side, 1 outlier on the low side. And then it's a little bit of skew to the right? We're gonna have a longer right tail here, so it's skew to the right. And then if you look at the rear wheel drive, no outliers. And again, it's skew. This one is has a much larger skewness. So still a higher skewness to the right. So that's how you compare different kind of like box plot for three different drivetrains about a city mileage. Now we can put in more arguments. Again, I'm going to recycle this code and just copy paste and then just put in more arguments here. So xlab. I did it earlier, so I'm going to just copy everything from here. Actually, drivetrains. Okay, xlab is about drivetrains. Copy that code and come back here. So we put in xlab, ylab, main. It's here. and its drive trends, MPG, CT versus drive trends. And I'm putting more arguments. It's the main titles, drive trends. X-axis is drive trends. Y-axis the city mileage, right? So miles per gallon per city. And then I'm putting a little bit more argument. PCH between I'm putting PCH 10, which is the size, right? The size of the and CX equal to 1, comma, and then I'm going to keep everything else the same as the previous one. Now let's run the code. It looks like we get a okay, so still the same graph, but with a different specification. And we change the style of the circle here. Yeah, and then basically we see the pretty much identical graph. But again, we can do a lot of different modifications here based on the box plot. Now let's create a scatter plot. Right, that's also another important graph called scatter plot. So we do plot CTY, curly wave, displacement, data equal to MPG. So we will look at the city mileage based on the displacement in the MPG data set. Let's see what that looks like. And then this is what a scatter plot looks like. As you can see, in this graph, it looks like there's a negative correlation between the displacement and then the city mileage in the city, right? So as the displacement increases, then the mileage CTY decreases. That's what we see here. And then I would say this is probably median correlation between the displacement and also the CTY based on this graph. And then we could, again, we could do a little bit more modification. I'm gonna copy this and then put in a little bit more arguments after that. Let's say we do X lab, double quotation mark, displacement meters. And Y lab, call this miles per gallon. CT. And name is the main title, MPG, CT versus engine displacement. PCH using 20 this time. And CX as a style. And color, we're using green this time. Okay. And let's run the code. Let's see what it looks like. And as you can see, we get a same graph, but with a little bit more details. And the contracts look good, right? The graph stands out. And then same pattern here. All right. And in RStudio, And then we can also plot the sine function. Let's say we can plot any function you can think of, right? Sine function, and from 0 to 2 pi, 1 period. Or you can do minus 2 pi to 2 pi, right? 2 period. That's doable. And let's run the code, and you see the 2 period of the sine functions from negative 2 pi to 0, and then 0 to 2 pi, 2 period. And we can also plot, let's say, exponential function with base e. So you just type exp represent exponents with base e. And for negative 5 to 5. And then let's run the code. Yeah, it looks like this. Yep. And then also probability density function. Right? We're going to take a look at the probability density function, maybe standard normal curve. Let's plot probability density function. No, it's normal distribution, right? Density function for normal distribution. Norm means normal distribution. From negative 3 to 3. 3 standard deviation. So z-score from negative 3 to 3. Okay. Let's see how that looks like. And then you see the bell curve, right? Standard bell curve. Z-score negative 3. And also, let's say we want to modify the graph, right, with a little more arguments. We're still going to do minus 3 to 3, and then put in the color equal to line. LWD I put in light blue. LW is thickness, right? Thickness of the bell curve. LWG is 10. Main title, standard XLab, x-axis, call this z-scores. Y-lab, it's the density, which is probability. Right? Density is same thing as probability values. Let's see how that looks like. It's one code, and this is what the graph looks like. If you feel like this is too thick, modify the thickness of the graph. So basically, you could customize any graphs you like. Now let's take a look at. Let's say you want to run a normal distribution, calculate the probability values for normal distribution. So given normal distribution with mean 100 and deviation 10, we calculate the probability, which is for this probability value for x value is less equal to 108. So basically, we're using this code called P-norm, meaning probability of normal distribution. So here Q is the x values 108, means 100, standard deviation 10. Right? You can just copy this, and now we're gonna paste it and run it right here. And then run it, you're gonna see probability value is 0.788146. So basically, we have 78.81% chance of getting the x values less than 108. And second part, we want to do same context. So we want to calculate the probability for x value greater than 108. So greater than meaning we want area to the right. So you're going to use the total area 1 minus area to the left. Right? So in this code, we need three things: Q, which is x values mean, standard deviation. So here just do 1 minus P norm. Probability of a normal distribution. Again, Q is 108. B is 100. Standard deviation is 10. So it's area to the right. And then if you run the code, you get this, right? So exactly 1 minus the previous one. And then if you want an area in between, we're going to do, let's say, between 94 and 108. So you do put in 108 first, and then put in 94. So then we get area in between. One more time, you do P norm. Q equal to 108 first, of 100, standard deviation of 10, minus P norm. Now the value is 94. Smaller x values, V is still 100. Standard deviation 10. And let's run the code. Then we're going to get area in between, which is 51.39% of chance the x value is between 94 and 108. We can also run a binomial distribution. Let's say this is the example we have here. So a bank knows that historically 1.2% of transactions in certain category are fraudulent. They monitor 500 random transactions today. And what is the chance of seeing exactly 5 fraudulent ones? So we do this density function for binomial distribution, right? BIOM means binomial distribution, and D means density. So we're looking at exactly 5. So we're looking at the density function at x equal to 5. So this is basically the code. The density function of binomial and x equal to 5, right? So the size is 500, sample size 500, probability of success 0.012. And yeah, let's see how that goes. And I basically calculated binomial values here, probability values for binomial distribution. So we have a 16.12% chance, right? This is happening. And then also, let's look at the other one, right? So what's the chance of seeing at least 10 fraudulent ones? So you do. So here we're using P, right? Meaning we are accumulating everything below at least 10, meaning 10 until all the way to 500. That's a lot of calculation, but we could do 1 minus 1 fraudulent, 2 fraudulent, all the way to 10 fraudulent. Right? So then we do 1 minus. Here is a probability of binomial distribution, meaning we are accumulating everything to the left below 10 and using 1 minus that's area to the right, and that will give us the probability values. So the probability value turned out to be 4.60% chance, right? At least 10 fraudulent. So the chances are pretty low. Now let's switch gear to another embedded data set called IRIS. So I'm going to put question mark IRIS to do a little research on the IRIS data set. This is a very famous data set. Let's run the code. And then right here, you're going to see this is the IRIS data set, famous Fisher Anderson IRIS data set. Give measurements in centimeter of the variable simple length, simple width, petal length, and petal width, respectively for 50 flowers from each of 3 species of iris. So we have Setosa, versicolor, and then virginica. And you have a more detailed information here, right, about this data set. And let's run some analysis here for the IRIS data set. Okay, so now let's do a quick plot. That is plot IRIS. run the code. As you can see, we'll get this scatter plot matrix. So this one gives us a lot of information, right? So we have different kind of like variables, sepal length, sepal width. So this first column is sepal length, right? On the horizontal scale is a sepal length. And then sepal width. So first graph is horizontal scale is sepal length. Vertical scale is sepal width, right? So we see the correlation matrix, all these different variables. And if you look at this graph here, it's horizontal is a species, right? 3 different species: Setosa, versicolor, virginica. And the vertical scale is petal length, right? So we have different measurement of petal length. This is basically what the scatter plot matrix gives us. And then also we could look into each individual ones, right? Say you just want to do a quick plot on the species. Let's see what that looks like. It's running, then you can see you get this. This is called a box plot, right? Box plot on Setosa, versicolor, virginica. They all have 50 flowers, right? Each species. And then also there's plot rich data set based on petal length. Let's see what that looks like. A scatter plot of 3 different species. First block is right here is the Setosa, versicolor, and then virginica. As you can see, the petal length increases from Setosa to versicolor, right? Increase dramatically, and that slight increase from the versicolor to virginica. So virginica has the highest petal length, and the Setosa has the lowest petal length in general. All right, so now let's do this. Plot iris, a little bit better graph of species. Iris $sign. You can specify the both variables, petal width, right? Species on the horizontal, petal width on the vertical. See how that goes. And we basically generate a box plot, right? So the R3 will pick a possible, the best possible graph for us. You see 3 different species and generating a box plot for each different species. It looks like for Setosa, it's skewed to the left. And for versicolor, it's slight skew to the left. No, actually slight skew to the right, right? Slight skew to the right. Same thing for Setosa, right? Have a skew to the right with the 2 outliers. And here for virginica, it's normally distributed. Look like normally distributed. One feet curve here. And then let's see. Plot. Create a scatter plot. Horizontal scale is petal length. Vertical scale is petal width. See the correlation between the petal length and petal width. See what happened. As you can see right here, it looks like petal length for the Setosa, that's pretty strong, right? Correlation between the petal length and petal width. For the versicolor, similar, right? Pretty strong correlation. And then for the virginica, I think it's a little bit weaker. It's medium correlation between the petal length and petal width. That's what we see from the graph. Now let's do the same plot, but with a little bit more argument. So let's copy this code one more time. Just build based on this code. And I put in more arguments after that. put in color, put red, PTH size. This is style of the shape of the each point there. In its iris, the length versus width, xlab x-axis, petal y-axis, ylab, petal width. Let's see how that goes. Let's run it and existing key. Let's get this graph right here. So petal length, petal width. Now let's create some more histogram, right? So histogram on each variables here. Start with the sepal length. Let's run the code. Looks like this is the histogram for petal length. And it looks like we have a almost, right? It's a little skewness, right? A little skew to the right. Because our data value are concentrated between 3 to 6.5. I think it's 4.5 to 6.5. That's where the majority of data value is. Now, let's look at create histogram on sepal width. What that looks like. Let's run it. And this one, it has a normal distribution, right? But there's a couple outliers here. These two are considered outliers, but generally speaking, this is a normally distributed, pretty close to a normal distribution. And now let's look at $sign, petal length. And this one definitely have a very, and yeah, definitely there's no clear pattern here for petal length. But if you just focus on, so this, if you consider 1 or 2 as outliers, and if between 2.5 to 7, we have a little bit, probably close to normal distribution, right? Something close, but not exact. And then also let's look at the last, meaning so far all 3 different variables behave differently in terms of distribution. Let's look at the petal width, the last variable, and look very similar, right? Petal length, again, we get this between 0 to 0.6 look like it's outliers, and then from 0.8 all the way to 2.5. Those probably have a skew to the left, right? A lot of data values are concentrated on this side. So that's a skewness, but again, very irregular distribution here. Now, we can look at other ways of creating histogram. Then it's a lot more professional, right? A lot more sophisticated way of creating. It's using ggplot. ggplot is the main tool. It's embedded under the ggplot2 package. ggplot iris. Statics is where we put in the x variable, the sepal length. And then here we put the second argument called geom point, geom histogram, indicating we want a histogram. So by default, they will present 30 boxes, right? 30 rectangle boxes. Let's see. Again, it's all blended together. It doesn't look nice. So we need to modify a little bit, right? At least for the folder, separate this graphs, different boxes. Now, next thing we're gonna put in same argument, pretty much just putting the different color for the here color. I'm putting green. Let's see how that looks like. Run the code one more time. Now on the border, they give us the green color separate this, and this is a slightly better graph, right? And we see the distribution here. Again, it's not a very good structure here, so you don't see a very clear pattern. Maybe it's a little, I would say probably it's a little skewed to the right, right? Because a lot of data value are concentrated in this portion right here. But again, this is not a very clear pattern. Now, let's look at the same graph, but with more arguments. I'm going to here build based on previous one. Here I'm putting the red color to fill the box. And I'm going to change the number of the beans to 20. Okay, let's see how that works. Give us a better graph. Looks like this is it presents slightly better pattern here. We have a look like that's a little feeding the curve here. It looks like probably close to normal distribution. In this case, and we condense the number of the beans, number of boxes here. All right, so that's basically what you can do to modify this box plot. And then we can create a different type of that graphs, right? Let's say we're going to create a frequency polygon here. So do ggplot Irish that x on parentheses x is equal length. Now the second argument, instead of putting g on histogram, we put in g on frequency polygon. And beans 20 boxes, 20 beans, color, let's say equal to blue using blue color. Let's see how that goes, right? So generate this frequency polygons to show how the frequency varies, right, from different kind of like measurements. It's a similar pattern to the one we just see in the histogram. Right. Now let's pinpoint down to each individual species and then create a histogram for each species. Right? So this is how we do it. So first of all, we type in histogram Irish. We're gonna plot the petal width for Setosa first, petal width, and open the square bracket and then put in Irish $sign species, and put couple equal sign and then put in Setosa. Now we are only graphing the Setosa species in terms of the petal width. X limit from 0 to 3. Breaks meaning how many boxes using breaks, it's library breaks. And the main title is the title width. Satosa. XLab, leave it blank. Color, I'm using let's see what kind of a graph we're going to generate. So we come up with this graph, right? Just the histogram for the Setosa species. Looks like this is has a very high skewness right to the right. So similarly, we will apply the similar code for the other two species. So here we just need to modify a couple of things. Right? Species here, just change it to first color. And everything else stay the same first color, just change title to first, main title to first color. And I change the graph to purple, right? The color to purple, and see how that goes. Now you can see now this is the distribution for the first color. And still skew to the right. I have some skewness to the right. And then similarly, create the third one, which is for the Virginica. So just change species to Virginica. Let's change the color. This one I change green. Okay. Now let's see how that goes. And then as you can see, you get this, right? And this one, I think is just a little skew to the left. It's not normally distributed. Okay. A lot of data value are spread here in this region right here. Right, so that's basically how you separate three different species, right? And then create a histogram for each. And come back to do some more Bayesian analysis on average, get basic statistics. So if you do add average, you're gonna get on the code, you see the sepal length, sepal width. This is the flower number 1, and then petal length, petal width, also the species, right? So you see the first 6 rows here with the title. If you want to do a quick summary of average, you can do that. And you see, first 4 variables, sepal length, width, petal length, petal width are numerical variables with a different file number summaries. Like sepal length, you have minimum, Q1, median, and then Q3 maximum. It looks like since median and mean are so close, so the sepal length you can assume a normal distribution. And similarly for sepal width, right, very similar. The mean and medians are so close. But for petal length, mean and median varies a lot. So there's no normal distribution here. And then similarly for petal width, median and mean. Median is a lot slightly bigger than the mean. So that's a little skewness here. And for species, there are 3 different species. Each one has 50. And you just look at each individual like summary statistics. Let's say we want to do species. Right? We see the breakdown of 3 different species. total versus color. And you're going to do a summary on the sepal length. You can also do that. And give us file number summary. So 4.3, Q1 5.1, median 5.8, mean 5.843. Difference as a minimum. Quartile 3, 6.4, maximum 7.9. Yep. So basically you can get any like summary statistics, like file number summaries for each variable. Let's say petal length. You can do that as well. And run the code, look like that, and then that's a median is much bigger than the mean. Now let's create more scatter plot, right? Using a ggplot, main package ggplot. Still based on the iris dataset, that x variable is sepal, y variable is sepal length. And then we will generate this geom point. Geom point indicating is scatter plot, meaning you can see all those points on the Cartesian system. So scatter plot. Let's run the code. I'm going to see this, right? If you look at all three different species, look like that's no very clear pattern, but if you break down in three different, each individual species, there's going to be a linear pattern. But when combine all three, we don't see a very clear pattern here. So that's something we have to look into later. Okay. So now let's generate a slightly better graph by just copying this. Let's copy the whole code and then just putting one argument, which is the color points. Let's say I put in the orange color. Let's see how that looks. And as you can see right here, we just see a different identical graph, but with different color. And again, we can build more arguments here. Still use the original code. And here I'm going to put in both labs. Here we could put in x variable and a y variable graph. X variable is sepal width. And y variable is the sepal length. And title is irises. You can give a title here, irises, iris. And let's run the code. Still, almost identical graph. But now we have titles like title here, horizontal axis, vertical axis, table. Now we can do something else right here. We use all the code, but we're gonna separate this different species with different colors, right? So here I'm gonna put color species under the aesthetics, AES. X variable indicated that, Y variable is indicated, color will be by the species. So we're gonna separate all three different species and see how that looks like. Yeah, now, right, I have to get rid of this geom point here, color geom point. Otherwise, you just show the same color. Right. So now you see, once I get rid of that, it's separated by different species using different colors. So if you look at it, now it's much better. So the red one is for Setosa. As you can see, there's a clear linear pattern, fairly strong, right? And the green one is for the first color. I think it's a medium. It's weaker compared to Setosa. Now Virginica similar. There's similar pattern in Virginica. It's probably medium correlation between sickle width and sickle length. But again, there's a way to separate all three different species. And then Setosa has a best correlation between the sickle width and sickle length. And then we can also change the shape of the species. So instead of using color of the species, we can use three different shapes. So use a color to shape. Now it R will give us different shape for different species. Right here, right? So the circle one is for Setosa. Triangle, right triangle one, equilateral triangle one is versicolor. And then the box is for the Virginica. It's separated by different shapes. But similar patterns here. Now I'm going to put in linear pattern. We try to model that using linear patterns. So Geom smooth under Geom, I'm going to create this using this previous code, this code right here. And I'm going to put in last argument, which is called one more argument called Geom smooth, meaning I'm asking RStudio to put a linear model for each species. Let's see how that goes. Now, as you can see, if you type in this ggplot iris, aesthetics, x variable sickle width, y variable sickle length, color equals species, and then geom point color is orange. Okay, I'm going to get rid of this argument. I want the same color, all three different, and I put in the labs. And Geom smooth method equal linear model, right? We're going to feed in linear model for each different species. So I'm going to run it one more time, and then come up with, so give us a much better graph. As you can see, we get a linear model for Setosa, the red one, the green one, versus color, that's a linear model, but a weaker. For Virginica is the blue one, and then it's weaker. So that's basically how we can generate linear patterns for each different species. One more time, just modify this. The Geom smooth, I put in one extra argument as e equal to force. And let's run the model one more time. I'll still adjust this, right? Get rid of shadow in the background. So give us much clearer linear model for each species. Again, still Setosa has the strongest correlation between the sickle width and the sickle length. And the other two is between median and weak, right? It's very close median correlation. Setosa has a strong correlation. And I'm also going to show you guys how to create a box plot. Use a different arguments, different code for Irish dataset. One more time. So box plot. I'm gonna create a box plot for SQL length with the different species. The data is Irish. Name is box plot of SQL length by species. I'm typing xlab, which is x variables, species ylab, SQL length. Also color using just blue. One like blue, give a different color code if you like. And let's run it and basically get this. Boxplot for if so Setosa normal distribution, right? For verse color, still normal distribution. Virginica is a little still to the right. Yep, and then with a little outlier on the low end, right? That's basically just a breakdown of the distribution of each species. All right, now let's create this. Just create a box plot for another variable called SQL width. I'm gonna reuse the previous code. Now here I'm changing the width, retyping everything. So box plot of the SQL width by species, SQL width, observable SQL width, and then color. I'm gonna put in light green. Okay, let's see how that looks like. We're gonna analyze the distribution one more time. One outlier here on the high low end for Setosa, and this is skew to the right. A very long right tail here. And here this reverse color is slight skew to the left, right? And then Virginia has a normal distribution, symmetrical with respect to the median. And so that's a breakdown of the and let's take a look at petal length. Let's also run the code for petal length. Here, petal box plot of the petal length. Compare the distribution. ylab is petal length. Choose the color to red. Okay, let's see how that goes. Look at the distribution here. It looks like Setosa is normally distributed. A little outliers here. And verse color probably close to normal distribution. And Virginica is a little skewed to the right? Just a little slightly skewed to the right. So that's basically distribution for the petal length. And one more time, we're going to look at the petal width. let's modify the code quickly. And title is title. I'll use different color. Purple for that. Let's see how this one goes. Run the code and zoom in. This and it looks like those has a couple outliers, circles outliers, and it's skew to the left. No, skew to the right, right? There's a longer right tail here. First color, a slight skew to the right, right? Skew to the right. And then a Virginica is closer to a normal distribution. That's kind of like how we distinguish three different species in terms of distribution. And the very last thing, I'm going to show you how to install this psych package. We're going to install this package called psych package. I'm going to do a summary statistics on the empty cars, right? Empty cars data set. So first of all, quotation mark psych package is called psych. Install that, and then also library of the psych. Execute this psych package. Now run. Now let's take a look at data set, right? Empty cars. So we put question mark empty cars, and let's run the code. And you see empty cars is model train car road tests. Data was extracted from 1974 Model Train US magazine. Comprises of fuel consumption and 10 aspects of the automobile design. Performance of 32 automobiles, 1973 to 1974 models. We look at it, first variable is MPG, miles per gallon. Second variable, cylinder, number of cylinders. Third variable, displacement, HP, horsepower, right? Fourth variable, stretch is a rear axle ratio. WT, 1,000 pounds. Right? QSAC is what they call a quarter mile time. Time it takes to reach the quarter mile. VS is engine either V-shaped or straight. And back in time as a transmission, AM means transmission, 0 automatic, 1 is manual. Here, number of the forward gears. And then carb is the number of carburetors. And this is a very famous data set. Let's run the summary statistics on this empty car. So we do this code called describe. Under the type package, there's a code called describe. Let's describe this empty cars data set. Run the code. And basically, you tell us for each variable, we will get variable number 1, sample size, the mean, the standard deviation, the median, the tree mean, right? This is tree mean, 10% tree mean. MAD is the median absolute deviation. And that's a minimum, maximum. Also the range for MPG, skewness, right? The bigger the number, the bigger the skewness. If the skewness is close to 0, that's good, right? It's close to normal distribution, no skewness. The bigger the number, and this one is Y skewness, it's positive, right? It's Y skewness. Kurtosis meaning how frequently does the data set peak, right? Reach the local peak. SE is the same error. All these useful summary statistics. We also do a quick correlation test. Do correlation test. on empty class, right? Meaning we want to see the correlation among all the variables. Let's see, and then basically you get this. It's sort of like a correlation matrix. Right? We end up with a correlation matrix. So there's a strong negative correlation between the cylinder and an MPG. Right, it's minus 0.85. That's a strong negative correlation. And also, MPG has a perfect correlation with itself. Right? That makes sense. Everything has a perfect correlation with itself. And also, MPG has a strong negative correlation with the displacement, strong negative correlation with the horsepowers, medium positive correlation with the stretch, strong negative correlation with the weight, and then medium positive correlation with the CubeSat, and then medium positive correlation with the BS, and a medium positive correlation with the air. And then with the gear, MPG correlation between MPG and the gear is medium. Correlation between MPG and the carburetor is negative. Medium correlation. So you can examine all these different correlations in this correlation matrix. So that will conclude this introduction to R videos.